Hi calculus classes. So again, I'm going to make the video for lesson 7.6. It generally takes 2 days, so I'm just going to make the whole video and then I'll kind of say maybe where day one might end, or you guys just stop it when you're done with day one or when you kind of feel like that's enough. But hopefully it goes well. Please keep working with each other, asking each other questions. If you have extra time on the day two, make sure you're using that class time wisely to work on homework. Use my answers online to answer questions. My plan is to be back on Friday, and then we have a question and answer day so we can work through some problems then. So. Lesson 7.5 was differentiation of all of those exponential and logarithmic functions. Lesson 7.6 is the integration of all of those topics. So you'll need to take out your green sheet, please. Take out your integration rule paper so we can fill in some more integration rules. Now I did realize yesterday when I made the 7.5 day notes that I gave you some formulas that you already had in there from previous chapter 7 notes. I just didn't realize that, so it's okay. We just revisited all those derivatives. And today we're going to learn some integration rules, okay? Integration techniques. So you'll need your green piece of paper. Also, I would take out the derivative piece of paper because certainly whenever you're doing integration, it may require a U-Substitution, which then means you're going to have to differentiate. So it's always a good idea just to pull out both sheets of paper. All right, in your notebooks, please. So we've got 7.6, logarithmic functions. Logarithmic functions and integration. So we're taking antiderivatives today and integration. So on your green sheet of paper, you are going to want to find this particular rule. It's like about halfway down the sheet of paper, that front side. We're looking for the integral of 1 divided by x dx. So please find that on your green sheet of paper about halfway down. And the integral of that is the natural log of the absolute value of x plus c. Okay, a couple things we're going to talk about. That absolute value. The reason it requires the absolute value is because you can't take the natural log of 0 or negatives. Now, just looking at the domain of the original function, it can't be 0 anyways because you can't divide by 0. So that eliminates that right from the original integrand. However, in this case, x could have been negative, but in order to apply the natural log piece of it, you'd have to have absolute value because you can't take the natural log of a negative. Now, so there's the rule that you're putting on your green sheet of paper. Now, I've had students ask me this. Why wouldn't you just use power rule for this? Why wouldn't you just have rewritten it? Now don't put this on your green paper because you're going to see why it's not good. But let's just start with it again. Many times we rewrote this as x to the negative 1 dx. Yep, we did a rewrite and then we would do power rule. So the power rule is you add 1 to the power, which is 0, divide by the new power, 0, it falls apart. We can't divide by 0. So power rule does not work for this because you end up dividing by 0. So what we had to do was come up with a new rule, which is this. Now that makes sense because the derivative of natural log of x is 1 over x. Yeah, there it is. Okay, second new integration rule. You're looking on your green sheet of paper and it's the next one down. The integral of a to the x dx equals. A is a number, x is your variable. So that's an exponential function other than e to the x because I believe, I hope we already had the e to the x one. I think we did in a previous lesson. So The integral of a to the x dx is, antiderivative of that is, you copy it, a to the x, times 1 divided by the natural log of a plus c. Okay, so the integral of a to the x is a to the x times 1 over the natural log of a, that's the base, plus c. Now, let's remind you that this, as soon as I put anything other than an x there, or anything other than an x there, it's going to require a U-substitution. So I only can take antiderivative of 1 over u, or 1 over x, or a to the u. As soon as that box is any bigger function, a function within a function, a composition, U-substitution is required. So there's the new integration rules. Let's go into your notebooks now and let's do some examples. So please grab your notebooks and let's do some examples. The directions are just evaluate each integral. Some of them are going to be definite and some of them are going to be indefinite. Evaluate each integral. Okay, number 1. Let's take the integral of 3 times 2x minus 1 dx. Now there's a couple different ways you could look at this and rewrite it. You don't have to. Some people like taking this coefficient of 3 and putting it in the front. Some people like just rewriting it like this. They'll put 3 times that quantity, or they just leave it like that. Any of the above is okay. Some people just go 3 times like that, 1 over 2x minus 1 dx. Some people bring it up front. Either way, it's all good. Now, what I'm noticing is that we have this function within a function. Remember what I just got done saying? If this piece underneath here is anything other than a straight x to the first, you have to do a U-substitution. Okay, so sidebar work. U is going to equal the inside function, or inside layer. That still holds true. What's going to be happening is this is the inside function for that division. U is equal to 2x minus 1. Okay, then over here you take derivative. du equals 2 dx. Okay, I got a 3, but I don't have a 2, so we just divide by the 2, or get 1/2 equals dx. So this is going to be replaced to the 1/2 du. Okay, change a variable. Change a variable going from x's to u's. Change a variable. So we've got the integral of either out front or in there, 3 times 1 over u times dx, which is 1/2 du. So there's the replacing of the variables with the u. Okay, I'm just going to multiply these together to make that coefficient of 3/2 times 1 over u du. So the antiderivative, thinking of the 3/2 out front, again, if you want to write it like that, go for it. Okay? So you're going to have 3/2 times the antiderivative of 1 over a u, because it is just a u, is the natural log absolute value of u plus c. So I took the antiderivative, and that's when you say plus c. Then, because the original problem had nothing to do with u's, you're going to put the x term back in. So it's 3/2 times the natural log absolute value of 2x minus 1, close the absolute value, plus c. And there's the answer. So you had to let u be that inside division. 3/2 times the natural log absolute value of 2x minus 1 plus c. Okay? Okay. Let's try another one. It's really interesting. Sometimes students like differentiation better, some like integrals better. It's really just a personal preference. 2. The integral of 4x divided by 4x squared subtract 8 dx. Okay, I can't legally divide that into that and that into that. If it was flipped, I could take 4x divided into each piece, but the way it's written, that's not legal. So I'm thinking I've got a function, this box right here, I've got this function within that denominator. So that makes the composition. So I'm in the sidebar going to let u be equal to 4x squared minus 8. So du equals 8x dx. Okay, a couple different ways you could handle this actually. Because it's 4x dx, I could divide by 2 and divide by 2 and make the 4x. I usually don't like to think that hard, like to make it match. I would just divide by the 1/8. Because this works out nice because they're multiples of each other. If that would have been a 5, changing the 8 into the 5 would be harder to think about. So I just do the same process every time regardless of how the numbers work. Okay, I'm going to actually do a rewrite so you can see the change in variable. So I'm going to rewrite the problem as 4 times, I'm going to do this. Yep, change my mind. 4 times 1 divided by 4x squared minus 8 times, and I'm going to group the x and the dx together. I'm making it so you can see the change in variable maybe just a little bit better. So I've got this 4 times 1 over that, and I put the x and the dx together. Okay, so now equals, here's the change in variable, the integral. Remember, every time we're still integral, still dx, good math writing. So 4 times 1 over u times x dx. Right there for my substitution, that's 1/8 du. So if I multiply things together, I'd have the 4 and the 8 going to reduce to 1/2. You can either put it in the integral or put it out front. It doesn't make any difference. 1/2 the integral of 1 over u du. So then you're like, yep, success. That is a rule on the green sheet. 1/2 times the natural log absolute value of u plus c. As soon as you take the antiderivative, it's plus c. And then you fill the u quantity back in. 1/2 times the natural log, the absolute value of 4x squared minus 8 plus c. Okay, there's number 2. Number 3. I can get rid of the title, give me a little more room. Okay, number 3. How about the integral of x plus 5, that quantity divided by x dx? So generally before I jump to the U-substitution, I think about, can I rewrite the original problem to avoid a U-substitution or make it a little bit easier to work with? So certainly this is legal because it's a binomial times x. I'm going to divide x into each term. So it's x divided by x plus 5 divided by x dx, which then simplifies to the integrand 1 plus 5 divided by x dx. So you can either write it or think about it, but this is what I'm thinking about. I'm thinking about breaking this up into 1 dx plus this integral of 5 times 1 over x dx. So it is legal to break up a sum or difference into separate integrals. Multiplication or division, no way. But adding and subtracting, yes. So now, no U-substitution needed. The antiderivative of 1 dx is x plus 5 times the integral of 1 over x, no U-substitution, it is just an x. It's the natural log, the absolute value of x plus c. And I only need 1 plus c because a constant plus a constant is another constant. So no U-substitution needed. A nice rewrite was good. Okay, number 4. Okay, number 4. Let's do the integral of 1, actually change it to a 3. 3 divided by, I'm making this one up, I just thought of it. You know, you guys know I like that when I do that. So I'm thinking up one here. Let's do 7 minus 2x, the quantity to the 4th. dx, oh geez, dx, okay. So, I can't divide the 3 in. I'm not foiling it out to the 4th, even though some of you try to do that. It wouldn't help you. You can't divide it in, and I could make this quantity up there to the -4. This is legal. I can go 3 times 7 minus 2x to the -4 dx. But that doesn't mean if I foiled that out, they all have a negative exponent on them. No, that's bad. So either you're thinking of it like this or you're thinking of it like this. But in either respect, we need a U substitution. We have an inner function. So sidebar over here, U is equal to 7 subtract 2x. du equals -2 dx. Okay, so I've got that dx. So I'm going to divide -1/2 du equals dx. Okay, change a variable. Equals. Now again, it doesn't matter if I wrote it like that or that. So I've got the factor of 3 times, this was u to the -4 times dx, which is -1/2 du. Okay, so multiply things together. -3/2 times u to the -4 du. Okay, here's why I came up with this example that wasn't on my sheet, because this is a common error. Students, after they learn the integral of 1 over x or 1 over u is natural log, they think every time they have an x or a u on the bottom, it's natural log. No, only if it's to the first power. If it's to a different power, then you use power rule. So the only time it's a natural log is if it's divided by that quantity to the first. I'm just going to use power rule. -3/2 u to the, add 1 to the power -3, divide by that new power, -3 plus c. Power rule. Okay, multiply by reciprocal, little scratch work over here if you need to. -3/2 times 1 over -3. 3's cancel, negative, positive 1/2. So this equals positive 1/2 u to the -3 on the bottom. So I'll go a little slow. So this 3 simplifies to positive 1/2, u to the positive 3 flips to the bottom, and then finally 1 over 2 times 7 minus 2x, the quantity cubed plus c. Replace the x part. Okay, let's do a definite integral. We'll do a couple definite, indefinites, all that kind of good stuff. We'll flip to a definite one though. We haven't done a definite one yet. Please keep up with your homework. Remember, this chapter can get ugly with that if you don't. Number 4. Oh, wait, that was 4. See, I added 1. So number 5. I might get off. The integral of 1 to e, definite integral, of the natural log of x, that quantity squared, divided by x dx. So, we cannot bring this 2 down front. If it was the natural log of x squared, then the power can come down front. It's not the same. So what I'm thinking about is, I've got this inner layer, and certainly this integrand is too complicated. We've got too much product, too much quotient. It's going to need a U-substitution. So U equals the natural log of x. That's that inside. So the derivative du equals 1 over x dx. Derivative doesn't need absolute value, just 1 over x dx. Well, look at that. There it is, 1 over x dx. Let me rewrite it. So I'm just doing a rewrite of the original. 1 to e, this is the same as the natural log of x, the quantity squared, times 1 over x dx. So I just grouped what was in the blue circle. So now I'm going to do the change in variable. So this equals the integral of, we let that be u squared, and all of this is du. Now we're going to change the limits of integration, because remember, these are with respect to x, and that's a u. So if I put in 1 right here, let x equals 1, u is going to be equal to 0. The natural log of 1 is 0. You should know that one. So without a calculator, you should know that the natural log of 1 is 0. E. If we let x equal e, again, think about the natural log of e. The natural log of e is 1. You should know that without a calculator. So when we put in e, it outputs a 1 with respect to u. Okay, this is an integral we can take the antiderivative of. The antiderivative of u squared, using power rule, add 1 to the power cubed, divide by that new power 3, evaluated from the limits 0 to 1. And since I changed the limits, I don't have to go back to x. I can just fill in those numbers. So 1 cubed divided by 3 minus, 0 cubed divided by 3, or 0. So my answer, 1/3. Great, 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 great. Okay, so let's go back to another just indefinite one. We'll kind of flip-flop back and forth a bit. Number 6. I have like, I don't know, 3, 4 more, so you guys can feel it out, like what's good day 1, what's good day 2. So here's the integral. Remember, the more you see, though, the more you're going to be able to do on the homework. The integral of 5, 3x dx. So definitely, this is using that a to the x rule. But that rule only works as it is on the green sheet if it is just an x. So what you have is a composition up in there. You have to let that be the u. If it's anything other than an x, you have to do a u substitution. So the derivative du equals 5 dx. Bring the 1/5 over, 1/5 du equals dx. Okay, all right, so let's do change in variable. Equals the integral of 5 to the u times dx is 1/5 du. Okay, so again, this 1/5 can stay in there, or it can go out front here. 1/5 5 to the u du. Okay, grab your green sheet, look at, find the a to the x rule. So the 1/5 is right there. looking at your a to the x rule. Your a to the x rule is you copy it. So 5 to the u times 1 divided by the natural log of that base a, which ours is 5, plus c. As soon as you take the antiderivative and it's indefinite, you got to say plus c. Okay, let's clean that up. Well, 5u is on top, so it's going to be 5u, but u is 5x, divided by what's on the bottom, 5 times the natural log of 5 plus c. Lots of 5s. 5 to the 5x over 5 natural log of 5 plus c. Okay, awesome. Okay, we've got 3 more. Ready? 3 more. Okay. Number 6. The integral of x squared plus x plus 1 divided by the quantity x squared plus 1 dx. Okay, so this is, you're going to see in a minute, play out kind of differently. Certainly, you're like, well, maybe I'll try a u, because I'm dividing by this quantity. So great, I mean, that's a good thing to try. Try something. U equals x squared plus 1. So du equals 2x dx. I've got way too many x's up there. I don't have nearly enough to substitute the du in for. Okay, abort, doesn't work. I can't divide in, doesn't work, because I've got a binomial times the trinomial. So, when you've got a polynomial divided by a polynomial, and nice little single division doesn't work, like one of the earlier examples we had x plus 5 divided by x, but you could just divide x into them. This doesn't work. Also, when a U-substitution doesn't work, another technique, strategy, a process, is long division. Long division will make it so the quotient is something that are added or subtracted together, and then we can take the antiderivative of each. So, sidebar, we're going to do long division of this integrand. So x squared plus x plus 1 is being divided by x squared plus 1. So x squared plus 1 is dividing into x squared plus x plus 1. Okay, long division. How many times does x squared go into x squared? Just ignore that part. 1. Distribute. X squared plus 1. I have to line it up underneath its like term. X squared plus 1. Draw the lines. Here we go. Change the signs. So that cancels and that cancels, and we just have an x. So, how many times does x squared go into x? It doesn't. It's too small. Therefore, this is the remainder. This is the quotient, this is the remainder, divided by still that quantity. So the rewrite, this integral is equal to that division problem. It's the quotient 1 plus the remainder, which is x divided by x squared plus 1, dx. So it's a rewrite, it's a weird rewrite, but this integrand is equivalent to that. Now, here's why. Because if you make a common denominator of x squared plus 1 over x squared plus 1, guess what? Boom, you get that back. So it's kind of like we just simplified the common denominator piece. Okay, I'm going to divide this up into 2 integrals because I can, because of the plus sign. So you have 1 dx plus the integral of x divided by x squared plus 1 dx. Okay, that's going to be a piece of cake, just x. This, what's our strategy for taking that antiderivative? Well, it appears to me that this is going to be a great candidate now for letting that be a u. 1 divided by that layer. So if we pull it aside and do u equals x squared plus 1, du is going to be 2x dx. Well, that is awesome because I've got the x dx product right there. The 2 is an extra, so 1/2 du equals x dx. Okay, I'm going to come back over here, change a variable. Now, at this point, if you want to just take that antiderivative, you can. So equals, the antiderivative of 1x dx is x plus c. But if you take the antiderivative, the best math writing for that integral is to give a plus c. Plus the integral, change a variable here, 1/2 times 1 over u du. Okay, make sure you follow that. The x and the dx are being replaced with the 1/2 the du. I could have put them next to each other too. That's the 1/2 du. And then you have the 1 over that box of x squared plus 1. So you can bring the 1/2 out front. So you have x plus c plus 1/2 times the integral of 1 over u. Well, the integral of 1 over u, because it's just a u, is the natural log absolute value of u plus c. Look on your green sheet. 1 over u is the natural log absolute value of x. Okay, the two c's are just going to make one constant. So you have x plus 1/2 times the natural log absolute value of u, which back over there is x squared plus 1 plus c. Now, definitely that one had a different twist with the long division. But you can see why the long division was helpful. It broke it up into two integral sums, which then you could do a U-substitution on the 1. Okay, we've got two more. I don't know what number I'm on. I'm going to say 8, don't know. 8, because I'm not following my sheet anymore because I added some problems and subtracted some because I like them better. So let's do the definite integral from 0 to 2 of 1 divided by 1 plus the square root of 2x dx. Okay, this one looks hard. The square root of that quantity, so the radical's over it all. Well, I don't know what else to do but let u be that bottom. So let's start and see where it takes us. I don't know if I'm going to like this, because we're going to have to take the derivative eventually there. So, if I let u be equal to 1 plus the square root of 2x. Okay, let's take derivative, right? Because that's what we do. I'm going to rewrite this though. 1 plus the quantity, 2x to the 1/2 power. Okay? So du equals, the derivative of 1 is 0. You're going to have to use chain rule with this derivative. Bring the 1/2 down front, keep the inside the same, 2x, lower the power by 1, negative 1/2, times the derivative of the inside, which is 2, and then you have the dx. Okay, so let's walk through that one again. The derivative of 1 is 0. The derivative of this, because it's got an inner layer, is chain rule. 1/2, keep the inside the same, lower the power by 1, times the derivative of the inside is 2 dx. Okay, let's clean that up. That cancels. So we have 1 over the square root of 2x dx. We got this extra factor right there. Okay, now, I'm hoping, I'm just going to sit here for a minute And if we multiply, I get that we're not supposed to really put the x's with the u's, but I'm just going to show you this for a minute and see if somebody can, like I hope you guys are looking and viewing. If I bring this over, you're going to get the square root of 2x du equals dx. Now I can't have x's and u's connected, because when I do my substitution, my change of variable, it has to be all with respect to u. So sometimes we had to do this little trickery. Up here, the square root of 2x is equal to u subtract 1. The square root of 2x is equal to u minus 1 du equals dx. So now it's 100% with respect to u. Now, what I'm hoping is I can do a complete change of variable and it's only u's. So I'm going to come back to those in a second. Here we have 1 divided by that. What was that? U times. What is dx? Dx is u minus 1 du. Dx is right here in red, u minus 1 du. Okay, let's put in 0 for the x, because that's an x quantity. That's 0. Square root of 0 is 0 plus 1. So the u quantity is 1 when x is 0. Okay, now put in 2 for the x. 2 times 2 is 4. The square root of 4 is 2. 2 plus 1 is 3. Okay, I never have to go back to x now, ever. So if I rewrite this, we've got 1 to 3 of u minus 1 divided by u du. Do I have to do another u substitution? I hope to gosh not. I can divide u into each piece. So it's the integral from 1 to 3 of u divided by u, which is 1, minus 1 over u du. So now I'm just going to take the antiderivative of each piece individually. Antiderivative of 1 du is u minus the natural log absolute value of u, no plus c needed. This is the 1 over u rule, evaluated from 1 to 3. So we're going to fill in the top, fill in the bottom. Equals, bracket, 3 minus the natural log absolute value of 3 minus, fill in the bottom, top minus bottom, 1 minus the natural log absolute value of 1 equals. Okay, that's just going to be 3 minus the natural log of 3. I don't need absolute value anymore because I know it's positive. If you kept it, it's not wrong, just kind of looks weird. The natural log of 1 is 0, so that's gone. And then you distribute that negative 1 through there. So this is 0, natural log of 1 is 0, opposite of that 1 is negative 1. So combining like terms, 2 minus the natural log of 3. Box it. Okay, one more. Number 9. I will say this is a lot more fun when you guys are here. It's not so much fun by myself. Number 9. The integral of e to the x divided by e to the x plus 4 dx. So I can't, like in the last problem, divide and break it up into separate pieces because these are the wrong way. It's e to the x divided by the sum. If it was the sum divided by e to the x, then I can divide. So, I gotta do a U-substitution then. I don't have another idea. So I feel like this is the inner layer. We're dividing by that quantity. U equals e to the x plus 4. Remember over here is derivative. So the derivative, du equals derivative of e to the x is itself, e to the x. The derivative of 4 is 0, dx. Oh, that's the best news right there. E to the x dx, right there, is du. So if I write the integral with a change of variable, it's going to be 1 over this box, which is u. 1 over u times e to the x dx is du. Well, that is something on the green sheet we can take the antiderivative of. It's the integral, oh, not integral, we can do it. Take antiderivative. It's the natural log, the absolute value of u plus c. Don't leave the u in, replace it. The natural log, absolute value of e to the x plus 4, close the absolute value, plus c. Box it. Okay. Now, I have seen some people on their green sheets put the u rule also on there. So that line on your green sheet where you have the integral of 1 over x dx, and we said that equals the natural log, the absolute value of x plus c. On that same line, people have done this. The integral of 1 over u du is equal to the natural log absolute value of u plus c. Just so they remember, if it's an x, it's an x, if it's a u, it's a u, but that is okay. The same thing like they've done where you had the integral of a to the x dx, which we'd said earlier in the notes, is copy it, a to the x times 1 over the natural log of a plus c. So on your green sheet, but then kind of on that same line, they just change it to respect to u, so they remember that as long as they get it back to just a u, the pattern is the same. It equals a to the u times 1 over the natural log of a plus c. That's really sloppy. Okay? So if you want to add that to your green sheet, like the u ones, so it's easier for you to remember or deal with when you do a U-substitution, that's great, totally fine. Okay, I think that wraps up our integration rules for logarithmic functions, which are the 2 new ones. And again, you just have a ton of problems, practice. Try to do as much as you can, maybe without looking at the answer sheet online first. Give it your best effort, and hopefully we'll be back together soon, and then I'll be able to answer your questions. Okay? Thank you.